Welcome to Data Science Monster. In this video, we are diving into the fascinating world of autoencoders in Python. We are in the era of generative AI, so it is really important to understand the concept of autoencoders. So, what are autoencoders? Autoencoders are a type of neural network used for unsupervised learning and dimensionality reduction. It is being used for several tasks like image compression and anomaly detection. But what makes them special? Let's now find out. At their core, autoencoders consist of two parts. One is encoder and the other one is decoder. The encoder learns to compress data into a compact representation and the decoder reconstructs the original data. So basically, you can think of it as a data compression algorithm learned by a neural network. So let us now proceed with the algorithm. So to do that, first of all, we are supposed to import the necessary libraries and packages. I have imported NumPy, Matplotlib. From keras.layers, I have imported input and dense. From keras.models, I have imported model. I'm going to use a very popular MNIST data set. So we have just done with the importing necessary libraries. So which data set we are using is very popular MNIST. I'm repeating it. What is the use of MNIST data set? What is the problem statement of MNIST? So basically, it would be having images of handwritten digits. The handwritten digits could be from 0 to 9. So in this data set, you can see train data as well as test data. So I'm loading the MNIST data set xtrain xtest equal to MNIST dot load underscore data. So once I have loaded the data, just I'm showing you how the data is looking like. For example, I'm displaying for xtrain 5 rows and 5 columns. So you can see that the different numbers, right? 0 you can see, then 51, 159, you can see different numbers. So the numbers would be ranging from 0 to 255. So what is this? This is nothing but about the pixel, right? You can see that the pixel values are ranging from 0 to 255. So what I'm going to do now, I want to normalize this pixel values. So I want to normalize these pixel values from the range of 0 to 1. So how I can do that? I can divide it by 255. Why by 255? Because in the previous step I said that the pixel values are ranging from 0 to 255. And also you can see that here it is integer data type. So what I'm doing now, I'm using or I'm converting it into float and then dividing it by 255. So now if you check your data set, you can see that the output would be ranging from 0 to 1. Right? You can see that the output would be changing from 0 to 1. So now if I check the shape of the train data, there are 60,000 training images and it is of 28 cross 28 pixel, which is nothing but 784. The test data, we have 10,000 images. Again, it is of 28 cross 28 pixel. So what is the length of the train data? That is 60,000 and this is about the pixel. Hope it is clear. So the first step, we have imported the libraries and packages. Then I have loaded my data set. The third step, what I'm doing, I'm normalizing the data. Now then what we can do is, we have to flatten the images. So to flatten the images, we are supposed to use reshape, and you can see length of X string, which is nothing but 60,000, comma, then I want to product from the first column, because from the first column, in the sense that would be like 28, comma 28, which is nothing but 784. So what I'm trying to do over here, I'm trying to flatten the images. So the MNIST was of 28 cross 28 pixels. So I want to flatten each image into a one-dimensional array of length 784, so that we can use it as an input to a neural network. So the reshape is done on train data as well as test data. So let us now define the autoencoder architecture. So first we need to pass the input, which is 784. So why it is 784? Because we have discussed that 28 cross 28. So an input layer with 784 neurons corresponding to the flattened image size. Then encoded layer with 128 neurons and a ReLU activation function, which is going to compress representation of the input. Then decoding layer, you can see a decoder layer with a 784 neurons and a sigmoid activation function. So this one is going to reconstruct the original input. This is what we have discussed here. Autoencoders has encoder as well as decoder. Now we are giving the input. That is what we have discussed. The input is given to encoder, then it gets compressed, then it is passed to decoder, then we would be getting reconstructed input. So now so far we have done this, right? We have defined the autoencoder architecture. So we have written encoder, decoder. Let us now do autoencoder. So here we need to pass model, then this input, right? And also the decoded one, right? Then we need to compile it. When I compile it, I'm using optimizer Adam and also loss binary cross entropy, right? So now this would be creating autoencoder model by connecting the input and output layers. Then the model is being compiled with Adam optimizer and the binary cross entropy loss function. This is what we generally use it for image reconstruction task. So let us now train the autoencoder. So you can see that we have instantiated with the autoencoder, right? So autoencoder dot fit, you can see like X train, comma X train. So basically, we use autoencoder on the MNIST data set. It uses X train data as both, you can see here, as the input and also for the target output, and using 50 epochs. So the batch size I have taken 256 and the shuffle is equal to true, which means that the training data is shuffled before each epoch. So once it is being done, after the training is done, the autoencoder is used to encode it and decode some images from the test data, right? You can see that. So once it is done, it would be taking some time. That is why I ran the code already. Once the 50 epochs are done, then you can see I'm trying to visualize the reconstructed images. So how many images I want to do? N is equal to 10, and also I'm specifying the figure size. so that you can decide for I in range n, the original image, right? So basically what happens here, this code visualizes the original test images and their corresponding reconstructed images. So the loop would be going through the first 10 test images and displays the original images on the top row and the reconstructed images in the bottom row. The final output of the code will be a plot that is displaying the original MNIST digit images and the reconstructions. So now we can visually assess how the autoencoder can recreate the input images. So now here you may be getting questions in your mind that we have given some values as input, right? 784. This I said 28 cross 28, so 784. So how do we come up with this, right? This would be basically changing according to the data set. So for this, it is working perfectly with 110, 128 neurons for encoder and 784 neurons for decoder. So hope it is clear to everyone. If you have any questions, you can put it in the comment so that I can respond to it in the upcoming video. Thank you.